His pupil, Democritus, coined the name atom. It means indivisible, because atoms were thought to be the smallest unbreakable thing. 2,400 years later, we stand among them.
Scientific discovery and reward come slowly. Ernst Ruska's work gave birth to the electron microscope in the 1930s. His Nobel Prize for Physics came almost 50 years later, in 1986. That year, he shared the physics prize with two other laureates, Gerd Binning and Heinrich Rohrer. Binning and Rohrer won the Nobel Prize for their work on the scanning tunneling microscope, the successor to the electron microscope. A scanning tunneling microscope can reveal atomic structure in surface features using a needle-like metal probe. The tip of its needle lets the observer distinguish single atoms. A scanning tunneling microscope works like this. The needle is lowered till the tip is 1 nanometer, 1/1000th of a meter from the surface of the specimen. Electricity flows across this gap between the needle and the atoms. To keep the current constant, the gap must be constant too, meaning that the needle rises and falls as it travels across an irregular surface. Light microscopes use optical lenses. Lenses of electron microscopes are electromagnets. Scanning tunneling microscopes work differently. Just as a gramophone needle turns irregularities into vibrations called music, a microscope needle creates pictures of surface atoms. This extraordinary tool was created specifically to study the characteristics of atoms. In this case, the microscope's sample is silicon. The resolving power is such that we can see each atom on the sample surface. For a long time, researchers have wanted to study atoms of silicon, the element whose properties form the very basis of semiconductor chips. The scanning tunneling microscope has at last made this possible. Researchers soon discovered that their wonderful tool was even more versatile. The microscope can move single atoms. Soon, scientists were drawing by moving them around. Researcher Donald Eigler decided to announce the microscope's artistic ability in a very personal way. Using just 35 atoms of the element xenon, Eigler spelled the name of his employer, IBM. The result resembles sandcastles drawn in atoms, not sand. The world's smallest letters were less than 5/1000th of a meter high. That was April 1990. By October, the Japanese NTT followed suit. Then JEOL in November, and JRDC in time for Christmas. But the Japanese letters were large by comparison. IBM retained its record for the smallest and the first. Before long, Hitachi fought back for the Japanese. In the fall of 1990, electrical engineer Shigeyuki Hosoki launched his attempt on IBM's record. For his try at writing atomic letters, Hosoki developed a method of his own. When the needle of a scanning, tunneling microscope is closer than normal to a sample, the electrical current firing across the gap drives atoms out of the specimen. The result resembles blasting high-pressure air at a dusty floor. Hosoki intended to use this property to remove atoms one by one, thus forming letters. He chose the very early morning of a November day for his experiment. There was no one around to clap, talk, walk heavily across the floor, or otherwise disturb the tiny denizens of nanospace. In less than 30 minutes, he finished his task. His letters read, Peace, 91. Shigeyuki Hosoki had successfully carved out the smallest letters in the world. Each one of these yellow peaks represents an individual atom of sulfur. Hosoki's letters were 2 nanometers high, beating IBM's record by 60%. 500,000 such letters in a row would form a line 1 millimeter long. This technology offers extraordinary possibilities. Some that come to mind are downsizing computers, increasing their memory capacity, creating new materials, investigating existing ones at atomic level to improve their strength or corrosion resistance. Nanospace has brought us to the threshold of a new technology, nanotechnology. For the past 50 years, the development of nuclear power has allowed us to harness the atom. Now we can see single atoms, move them, even build with them. Who knows what a future in the tiny, enormous worlds of nanospace will bring?